Hi, my name is Shreya Jaram, and this is my video for Physics 2212 Experiment 2 Magnetic Fields. Introduction. The purpose of this experiment is to determine the magnetic field produced by a bar magnet using an experimental procedure and a computational model. The fundamentals used in this lab are the Biot-Savart law, the distance dependence formula for a bar magnet, the magnetic moment formula, and the assumption that a bar magnet was acting as a dipole in this experiment. The final results showed that the bar magnet to have a dipole moment of 2.59, an n value of negative 3.04, and a k value of 5.18 times times 10 to the negative 7th, as well as a model of the magnetic field. So as mentioned before, this is the Biot-Savart law, and then this is the linearized version of this law. And then here we have the distance dependence formula of a bar magnet that says the magnitude of the magnetic field of a bar magnet is equal to k times r to the power of n. And then the magnetic moment formula says that mu is equal to k divided by 2 times mu naught divided by 4 pi. In our experiment, the initial conditions were that the meter stick and the magnetometer positioned orthogonal to Earth's magnetic field, and the bar magnet positioned at the end of the meter stick, with the system being the bar magnet and the surroundings being everything else in the universe. This was the graph that was created from the values that were found during my experiment. And using the linearized Biot-Savart law from this slide, we get this linear equation where the slope of the line is our n value and the y-intercept is the ln of k. So if you raise this to the with e to the power of this, it'll give you the value of k, which was determined to be 5.18 times 10 to the negative 7th. And then as we can see here, our n value is negative 3.04, which is our slope here. And then mu was calculated using the magnetic moment formula to get 2.59. And then these were the values that were found for the 45-degree angle measurements. Now in my code, I used my mu value from the previous slide here, and then this was the formula I wrote for, or the function I wrote for the dipole, and then the scale I used was 5e to e3 to have everything be shown in this. And then the distance I used was 0.26, which was similar to the distance for d perp, because I wanted all of them to be represented at around the same distance. As we can see here, I have the vectors for all of the axes, and then the arrows and all of that were calculated for each one. Here I have one of the examples for the on-axis and one for the perpendicular axis. And then this one is for the 45-degree angle one. So discussion. The off-axis B net calculated in the experiment was 3.78 e to the negative 5th, while the computational model determined it to be 2.27 e to the negative 5th, which is quite similar. Errors could be due to interference from other electrical or magnetic fields that I could not avoid, such as my phone itself, which I was using as a magnetometer, or my laptop, which I was using to record the data, and also from the Earth's magnetic field not being recorded exactly as it should be at my latitude and longitude, which would have skewed all of my answers slightly. The answer to the question asked in the experiment portion of the instructions is that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So discussion. My first what if answer is that if the setup of this experiment was at an intermediate angle rather than facing true north, the x and y components of the net force would have both had to been accounted for in on-axis calculations, and the results would have been far less accurate, as it would have been difficult to measure what this intermediate angle's value was. And what if, for my second question, if there had been two identical magnets rather than just one, the magnitude of the values would have likely doubled, as both would be enacting the same field in the same direction, thus making the magnitude twice the original. In conclusion, the Biot-Savart law, the distance dependence equation for a bar magnet, and the magnetic moment formula were all utilized in order to demonstrate the magnetic field of a bar magnet acting as a dipole. After taking the Earth's magnetic field into account, a bar magnet can be an accurate representation of the magnetic dipole. Thank you.